There is something I wanted to do for months, and I think now is finally the time for that. Well, to be honest, not my best peel experience, but fairly satisfying nonetheless. I nearly forgot that I ordered clear acrylic after working with that greenish protective film for basically more than a year. Which also means that it has been over 1 year since the last video of the series. Yeah, well, sorry about that. But as you can see, I've made some progress since back then. The CNC isn't completely finished, but it already has all the things needed so I can work efficiently with it, and there are only a few final touches necessary. So let me show you all the things that changed since the last video, starting from the top. Obviously, my MPCNC now has an enclosure. When using an air blast, like I do, an enclosure is absolutely necessary if you don't want to ask yourself why there are chips even in your bedroom. They get everywhere, and I'm talking out of experience right here. I use 20x20 aluminum profiles and 4mm thick acrylic sheets. 2 gas springs hold the enclosure at whatever position I set it. I got these from the engine hood of my car, and so far they work flawlessly and are fairly cheap as well. Thanks to the aluminum profiles, it's also easy to get them into the right position. 2 magnets in the front help to keep it completely closed, and the foam creates a nice seal so that no chips can get out. The air blast is basically just a cheap minimal quantity lubrication system where I pinched off the coolant supply and connected the air supply to a small compressor. It is screwed to a piece of angle iron, which also holds the new drag chain. On the MPCNC, it's important not to mount any additional stuff to the Z-axis, especially drag chains, as it is probably the least rigid part of the whole assembly. Use the XY centerpiece as a mount instead. The drag chain runs on a steel profile, which is mounted with a 3D printed part and the same screws which hold the motors. Nothing fancy here, but it works. Many of you have asked which spindle I'm using, and I should have probably mentioned this before. This is an AMB FME P 1050. So it's made by the German company AMB Electric, has 1050 watts of input power, and it's their P version, which means it has an ER16 collet chuck and a lower runout compared to their other spindles. But although it's better, it's not actually great. Mine comes with 0.02mm of runout in the cone. It costs roughly as much as a basic MPCNC, but I would buy it anytime again. The combination of small size, low weight and ease of use makes it perfect for the MPCNC. Additionally, it finds use in many other places in my workshop, for example on the lathe or as a handheld router. Some of you have already spotted these wipers in one of my last videos. When a roller moves over a chip that somehow got on the rail, it will result in a bumpy movement and a bad surface finish. These wipers take care of most of those chips, but they are not perfect as there are still ways for the chips to get in between the rail and rollers. However, it should actually be possible to completely seal the carriages, which would be a nice upgrade, especially when you want to machine lots of wood or plastics, where the chips tend to stick to the rails. The table is welded from 50x50 x 3mm square steel tubes and steel angles. As this was my first welding project, I am not eager to show you any close-ups. It is however a really nice and sturdy base for the CNC, although at some places I maybe should have measured twice. The wheels are great for pushing it around in my garage, and all there's left to do is to put some paint onto that thing. The electronics cabinet is a bit bigger compared to a usual MPCNC. I wanted to try some new things while keeping it easy upgradable and neatly arranged. It's an old PC case where I removed all the internal structures and added custom front and back panels, which obviously have been cut on the MPCNC. So yeah, 1mm sheet metal can be cut, but it's not a pleasant experience. On the top right there's an Arduino Mega with an RAMS 1.5 board. The motors are controlled by 5 TMC2208 stepper drivers, which are connected to the Arduino via UART. So setting up all the features like current limit, microstepping and so on can be done in software. Those drivers don't like if you turn off the input power while the motors are still enabled. Therefore, the emergency stop just pulls the enable pin of all drivers to a high signal, which cuts the current to the motors. Connecting all those pins to a single emergency stop switch is done by this board here. To the left, we got the low voltage power distribution and a relay board. On the bottom there's a 230 volt power distribution and 2 relays to control the 2 outlets, one of which is intended for the spindle. Then there is a 24 volts power supply for the stepper drivers, as higher voltage generally means more torque at higher speeds, a 12 volt supply for the fans, relays and maybe some LEDs in the future, and a 5 volt supply for the Arduino and Raspberry Pi, which is intended to run something like CNC.js to control the CNC without an additional computer. Currently this one isn't configured, as I like to tweak my cam setups a lot and therefore just directly stream the G-code from my laptop to the Arduino via Pronterface. Having 230 volt stuff so close to your microprocessor and signal wires isn't great, and same goes for the motor wires, which carry fairly big currents. Therefore, most of the wires which go in and out the RAMS board have EMI filter magnets on them. They actually do make a difference, because before I installed them, the Arduino would crash from time to time. Now to the double build setup, or rather, the missing double build setup. As I said in the beginning, it's probably overkill, and yeah, it is. There are 2 main reasons why I removed it. First of all, the belts are usually really dirty when you get them, and due to my insufficient cleaning, it started to curl away from the angle iron in some places. Additionally, the 15mm belt takes a lot of force to be tensioned, so much in fact that at some point it pushes the angle iron down and the belt snaps into the next groove. So setting up the right tension was always a bit tricky, and I tried many different designs, but in the end decided to just let go of the whole double belt. I didn't notice any performance drop with a single 9mm belt, and so I'm not going to switch back. Furthermore, I don't even think that belt stretch has a significant impact on the MPCNC. Here I am pushing against the carriage as well as the end mill, and you can see the deflection on the 0.01mm dial indicator. Now take a closer look on that pulley. To state the obvious, it rotates, so most of the deflection isn't caused by belt stretch, but instead because of the stepper motor, which isn't able to hold its position. And that's quite reasonable, as most of us are using 16 times microstepping, which drastically reduce holding torque. Bigger motors with higher torque would perform better, but also adds the need for more space and beefier electronics. Some people already brought up the idea of using lead screws for the X and Y movement. However, I would strongly advise against it. Most MPCNCs come with 300 to 1000mm of travel, and lead screws are just way too slow for these distances. I thought it would be a good idea to use a lead screw with only 1mm pitch for my Z-axis, hoping it would give me better accuracy or the need of less microstepping for the stepper motor. It actually just limits me to a painfully slow speed of 3mm per second, and I would highly recommend to use a higher pitch. Now that we got all the important stuff covered, I would like to address some of the most asked questions which haven't been answered in this video yet. For questions about feeds and speeds, end mills and so on, check out my latest video about cutting aluminum on the MPCNC. Let's start with the size. The work area is 600 by 275 by 75 mm, and including the table and the enclosure, the total size is 1250 by 680 by 1300 mm. All 3D printed parts are made out of PLA, which is the recommended material due to its stiffness. After nearly 2 years, some parts show cracks in highly loaded areas. I have added some superglue, and it seems like they are not getting worse. Those cracks could be avoided by smoothing out sharp corners, or not loading the parts along the layer lines, or by adding more space for washers. All of my modifications, like the wipers or belt tensioners, can be found in Thingiverse, the link is in the description. And last but not least, would I recommend this machine? This has been my first and so far only CNC router, and there was a lot back and forth before starting to build it. But even now, with most of the alternatives in mind, I would go for it again. The machine just makes sense. There's no part that is overkill or undersized. For example, using simple tubes as both linear movement and as a frame with inexpensive 608 bearings is totally adequate, as well as giving you the best value for your money. But don't get me wrong, the MPCNC isn't the perfect CNC. For example, getting the machine all squared up is fiddly, and I've already mentioned the problem with chips getting on the rails. Also, the size of my machine seems to be the sweet spot, and going bigger is going to reduce the cutting performance quite a bit. Obviously, I'm not going deeper into topics like accuracy, chip removal rates or similar. The MPCNC is a beginner CNC, and in the end you get what you pay for. And I'm very happy with what I got. If there are any questions left, feel free to leave those in the comments. Thanks a lot for watching and have a great day.